Hello, everyone. My name is Wang, and this is my colleague Mehrab, and we are on the system technologies and engineering team at ByteDance. So today we are going to present our idea about using transparent shared memory communication with eBPF to improve TCP performance. So let's take a very quick overview of the problem we are trying to solve and our proposal. So the problem we are trying to solve actually is we observed the TCP communication overhead is very high when we for the co-locating application scenario. And we want to propose to a new way to bypass TCP stack at the socket layer, and we want to use shared memory as a communication channel to bypass the TCP stack. And we want to leverage eBPF to maintain the transparency to all the TCP applications. And the result we have so far is we already observed about 12% throughput improvement for containers. And we believe we still have more room for further improvement. So before we start to diving into the problem, I think we need to take a look at the background. So the first thing I want to explain is what is shared memory. So shared memory today we are talking about is a very general concept. For example, if we use the same kernel, we use socket map. Socket map actually is also a form of shared memory as long as we share the same kernel. So and for the shared memory, I think we already know shared memory is the most effective way we could achieve within one computer system. And actually, shared memory is already commonly used for the inter-process communication in the operating system in general. So it's nothing new and nothing special. And also specifically for networking, actually shared memory is also common because we already have the RDMA technology, which is also a form of shared memory, and we should take it even further because it could also access the memory, the remote memory directly without even involving the CPU. So the question is here we want to raise is could we also leverage shared memory for TCP communications when the applications are co-located on a single computer system? And the next question actually is, because we are targeting about the co-locating application, so why do we still care about TCP? Why don't we just switch to other solutions? So the point here is, TCP is already, kind of the de facto standard for all the communication within data center. TCP is still dominant within data center, although, we have other UDP-based solution, like a Quick or maybe, Homa. However, TCP is still the dominant, in the reality. And because of that, actually, TCP protocol is also the choice for the applications when they want to communicate with each other or with different applications, TCP is still the choice. And because of that, actually the TCP socket API is also kind of become a standard API when we want to program our applications for the networking. So these are the reasons we believe TCP is still important and we still want to target TCP. So what is the problem we are trying to solve? So if we look at the problem here, actually the problem is essentially because of the TCP stack. We know TCP stack has many layers. This is good because TCP. This is good for the abstractions because because of this kind of layer-based abstractions, we can actually have a lot of optimization and different abstractions for different layer and different implementation for different protocols as well. However, this is also a problem when we talk about the specific case targeting the co-locating applications, because of these so many layers, this could be an overhead for the performance. So what is target scenarios we are talking about? The first case we are talking about is, the simplest one, the loopback. So for example, when we have two different applications and they are running on the same physical server without any isolation, their communication actually could, be just a shortcut with loopback. So loopback is pretty old. Actually, it's a very good optimization to optimize this specific scenario. However, despite we have this kind of optimization with loopback, we still need to go through. We still need to traverse the TCP stack twice. As I show in this diagram, and because TCP has different layers, we still have quite some layers to traverse for this kind of case. And another case actually we consider is the co-locating containers. So today, because we use containers a lot, and when we have two containers co-locating on the same physical server, we still have the similar problem. The only difference we have is, for containers, we have different ways to connect with the container, which is usually the virtual Ethernet device. However, despite we have this kind of optimization, we still need to traverse the TCP stack, and we still need to go through the most of the layers we have for the TCP/IP stack. And similarly for the virtual machines, so because we also use virtual machines, and when the virtual machines they co-resident on the same hypervisor, they still have the same problem, and the problem is even worse here because of the virtualization overhead we need to pay. Because for virtual machines, we do have the virtual devices set up for the network communication, and this overhead actually is higher than the container and also loopback case. So these are the three scenarios we target for our discussion and optimization. And let's take a look at about what other possible solutions we have today. So I listed four possible solutions we already have currently in the Linux kernel. The first one is Unix domain socket, which is also pretty old. So we already know Unix domain socket could specifically optimize TCP and without any layer, without any stack. So this is definitely better and faster than TCP. However, the problem with Unix domain socket is it has a different socket family. It also has a different socket address. So that means, the application, if they want to move from TCP to Unix domain socket, they need to change their source code. And similarly, we also have another possible solution, but specifically for the virtual machines is the virtual socket. So the virtual socket, also sometimes we call it vSocket, so which is also good, and also kind of has no layers, or has a very tiny layer or a very tiny header for the communication, but still better than the TCP communication. However, the problem actually is pretty much the same as the Unix domain socket. It's a different socket family. It has different socket address. And of course, we also have RDMAs, right? RDMA is, as we know, RDMA is super complicated. The API is, which we usually call it the RDMA verb, is much more complicated than the traditional socket API. So programming with RDMA is much harder than programming, just with the socket API. And also RDMA itself actually relies on the hardware support. So when we use RDMA, we definitely need the hardware, the NIC, the network infrastructure to support this kind of communication. And I think this is why, the recently, relatively recently, we have another solution, which is called shared memory communication over RDMA. So this solution actually is pretty good, in my opinion, because it clearly solves the problem of, the complexity of the programming with RDMA, because with the shared memory communication, actually it could actually still have the socket API on exposed to the application, and also it also combines with TCP together with RDMA, so that it could also kind of mitigate the limitation with of the RDMA as well. So from the user point of view, actually, users, they don't need to care about whether it's TCP or RDMA. It's just the socket API, and it could also transparently fall back to TCP if RDMA is not available, on with the hardware. And of course, if we want to leverage the advantage of RDMA, for the better performance, we still have to rely on the hardware support. This is for sure. And another thing I want to mention is actually this is not 100% transparent to the application, because the shared memory communication is a completely different socket family. So that's why they actually provide the LD preload to overload the socket family to overwrite the TCP socket family, to use this. So it's not 100% transparent. So what is our solution? So our idea actually is pretty much, combine, all the advantage and also get all the different inspiration from different places and put them together. And we want to target specifically for the scenarios we just mentioned in the beginning. We are not targeting, the remote TCP connection cases. So we still want to bypass the TCP layer, that's for sure, because of this kind of overhead. And we want to use shared memory as a communication channel. And ideally, we want to use zero copy, but zero copy is very hard. So I don't think we can just begin with zero copy. And more importantly, we want to be 100% transparent to applications, because we don't want applications to rewrite their source code, and we don't want applications to just specialize their source code, to target the container case, to target the VM case, or to target the bare metal case. And we get inspirations, from the SMC, and which leverage the TCP three-way handshake to exchange the information, to establish all the necessary information for the shared memory communication. And we also take a look at the eBPF infrastructure we have, and we get inspiration from socket ops and socket map as well. So our idea actually is overall is very simple. So we want to hijack the TCP three-way handshake, and we want to exchange some information during the connection establishment, and after that we all the later communication, all the data exchange will be through the shared memory channel. And the three cases actually, they are complicated, especially the virtual machine case. It's the most complicated case. So this is why we want to break we want to separate the three cases actually into two. The first two cases actually are much easier. So which we call it the non-virtual machine case. So this case is much easier than the virtual machine case. So for this case, actually, we want to break down the case into three pieces. The first piece is how we hijack the three-way handshake. So we could just simply leverage the eBPF socket ops, which already exists, which could work very well actually. And the communication channel, like I mentioned, the shared memory is a very general concept. So because this case, the kernel is shared, so as long as we share all the data structure actually is essentially a shared memory. So we leverage the socket map, which is a form of the shared memory, and we socket map actually leverages the SK message for all the communication. And to hook the send message, receive message, actually we also have something existing called the SK message vertex, which could actually just redirect all the SK messages to the destination socket. And after we investigated this, actually we realized that actually Selenium already has a very similar implementation, and it causes the implementation socket ops enable as an option for the Selenium users. And we did some benchmark with this solution, and we surprisingly got a very surprise result. The performance actually is much worse than TCP. So this surprised us. So let's take a look at what happened to this solution. So in Selenium, this solution actually sometimes is called a socket acceleration. So it's pretty much the idea that I just described. So the lessons we learned when we did the research is TCP actually is not as bad as it appears. I know I mentioned, TCP has many layers. However, on the other hand, TCP actually is pretty good at batching. So we realized the problem actually, the significant difference between this solution and the traditional TCP actually is batching. TCP is pretty good at batching. So, and TCP server actually has been optimized for decades. We have many Linux kernel developers in this room, and people are, spending significant efforts on optimizing the entire TCP IP stack. Actually, it's very well optimized. And on the other hand, like I mentioned, because this solution actually leverages socket map, which uses the SK message. So SK message is, to be honest, is not optimized at all. And specifically, on the other hand, the equivalent of SK message for the TCP is SKB. SKB is very sophisticated, especially for batching. I can give you a quick example here is the release shock. So in this function, actually, we do have some batching techniques for the SKB, which is batches all the SKBs in the backlog, which is very good. And on the other hand, we did further investigation thanks to my colleague Zijian. Actually, he did all the work here. So he actually noticed the bottleneck of this solution actually is the socket lock. So the reason why the socket lock is the problem is essentially the sender needed to acquire the receiver's socket lock for the socket accounting. So we will go to the details, and this turned out to be the source of all the problems we have. And fortunately, we do have some ideas for optimization, and also my colleague Zijian actually already finished the work, and we got some very good results. So the problem here actually, as I showed in this diagram, is the socket lock. So the sender needed to acquire the socket lock for at least for the socket accounting purpose. Because of that, the sender and the receiver they needed to contend for the socket lock, and this is the source of the problem. So the solution we have actually is pretty simple, actually. So we just want to introduce a worker. Literally, so maybe it looks like, we are just shifting the problem from one side to the other. However, it is not this case. So the reason why we want to move it to a worker is that so we could actually free the sender. And because we need to separate some work from the sender to the worker, that means we need to introduce some queuing for the SK messages. And because of this queuing, actually, we could actually also have some opportunities to batch all the SK messages as well. So this is actually the idea. Actually, this idea is pretty good, actually. So we got some very promising result. So although our code is not 100 complete, however, this is the evaluation so far we have. We already beat the traditional TCP/IP stack. So for the throughput, it's about 20% higher than the traditional TCP, and the latency is almost 30% lower than the TCP. But I believe we can do better. And for the VM case, I'm going to handle it to Mehrab.
Thank you. So as Cong mentioned, that VM case is much more complicated than the non-VM case. Because of the address space separation between the virtual machines imposed by the hypervisor. So for the VM case, we also break it down into three pieces. First, we hijack the three-way handshake. Basically, we play with the socket with TCP option. For the communication channel, we use a tool available for QMUK VM called Inter-VM Shared Memory, IVSSH-MEM in short. We also play with the send message and receive message hooks. For that, we use StackOps for Stack Proto. In the next following slides, I'm going to talk about each three of them in little more detail. But before that, we should mention that we have some security assumption, which is we assume that these VMs will be running our own known workload. So we trust the workloads. That means we trust our VMs. And therefore, we trust all the VMs running on the same host. We are still in the development phase of this work. So we don't have any prototype implemented yet. So let's have a very high level overview on the design. So we plan to use IVSSH-MEM to allocate a big chunk of memory on the host so that we can share it between VMs. And we plan to break it into smaller chunks so that we can assign one chunk per VM. Let's say we have two VMs, VM1, VM2. During the virtual machine creation, we supply the host IP address and chunk is the chunk we are going to assign it to, that chunk's offset and size. So let's say VM2 is running a server and VM1 is running the client. And in that case, the client will create two ring buffers on its assigned chunk, one for transmit, one for receive. During the three-way handshake, the client and server exchanges host IP and TX-RX offset information with each other. So that looking at the received host IP, they can identify if both of them are running on the same host, same hypervisor. So if they're on the same hypervisor, they can change their communication method to ring buffer based communication method. So later, once the connection is established, if the client wants to send any packets, instead of using SK message, it will put the packet in the TX ring and the server will read from there. Conversely, if the server wants to send some packets to the client, it will put the packet in the RX ring buffer and the client will read from there. Now, one virtual machine can have multiple clients. Okay. So in that case, there will be multiple pair of TX-RX rings. In order to keep one TX-RX ring separate from another set of TX-RX, we can implement a eBPF map where the key will be a tuple consisting of source and destination IP addresses and source and destination port numbers, which will act as an unique key. And for the value, we can put the offset to the ring buffers. So let's jump a little deeper in the implementation that we planned. So we use eBPF programs in the handshake process that hook during scene and act events. The eBPF program on the client side creates the TX and RX ring. Excuse me. So after the eBPF program on the client side creates the TX and RX ring, it sends the TCP IP and ring info to the server, and server matches the host IP with its own host IP. And after that, it can determine if the client is running on the same machine that it itself is running on. Now, if the host IP matches, they can establish the connection for using the shared memory for the further communication. Otherwise, the client will clean up these rings that it created initially if they are not on the same host. So let's talk a little bit about IVSSH mem, because this is what we are using for sharing memory between VMs. Someone may want to use something else if they find it more appropriate. So the IVSSH mem tool creates a shared memory segment and exposes the memory to multiple VMs as PCI devices. And the VMs receive the PCI address bar, and the VMs can map into those addresses to have access to the shared memory. Now, we need someone to use the IVSSH mem tool. We need someone to use this IVSSH mem tool to create the shared memory, divide the memory into smaller chunks so that it can assign one chunk per VM during initialization. Also, it can help us pass the host IP to the VMs during VM creation. We can also use BPF Arena that builds eBPF storage on top of these IVSSH mem chunks. And this eBPF storage works as backend for the ring buffer. Finally, the last part, stacked ops for stack proto. So in the non-VM case, from the non-VM case, we already have many hooks in TCP, BPF, and message for sock map. So in order to avoid further implementation of hooks, we want to introduce new stack proto with stack ops for more flexibility. So we plan to use eBPF program to implement all TCP socket operations. For example, send message, receive message, poll, close, and remaining. Now, these send messages will have their own implementation. For example, this send message can implement their own TCP send message for shared memory instead of regular TCP message send message that uses SK message. Instead, this send message will use ring buffer for sending packets. Similarly, the TCP receive message shared memory will use ring buffer for reading packets, receiving packets. Now, with these techniques, we can not only implement shared memory-based TCP, we can also build an infrastructure, possibly for other protocols like HOMA, shared memory communication sockets, multipath TCP, but this technique will still retain TCP socket APIs. So this is our moonshot. In summary,
here is a quick summary of our talk. So we put all the possible solutions together. We mentioned for other possible solution, and we put our solution here, and here is a very comprehensive comparison. So and this is all we have. So any questions?
So I know a lot of companies are working on encrypting memory between VMs. Would this solution work if memory is completely encrypted so the host itself cannot have insight into the VM memory?
Oh, this is a good question. We actually never consider the encryption case. So I'm not sure whether, the shared memory is encrypted for both VMs. If it is, I think definitely have some troubles.
Okay.
Yeah.
So I saw when you do the VM case, you were having, I didn't catch where, it looked like both clients and server were using the same queues from the VM. I wasn't quite sure if you could explain that a little more, or is there something that passes the address of like which chunk to use between the client and the server? Because I would have expected like VM2 would be accessing its chunk 2 and using a queue there, but I didn't quite understand that.
So VM2 would be uses its own chunk if it acts as a client. So it is client's responsibility to create the ring buffers. Otherwise, what will happen is if the server has to create ring buffers for each connection it receives, then the server has to create a lot of rings.
Yeah.
We want to avoid that.
Right.
So the client will create the ring buffers and it will share the reference with the server. So that if server has to send or receive something, it will use the ring buffer created by the client.
Okay, so that's part of that three-way handshake.
Yes.
Okay, thanks.
My question is, for VM use case, you actually want to steal pretty much everything, socket operation. Why the eBPF is even like needed there comparing to LD preload? Because it's basically what is you are like doing. So you are stealing all the connection and you still providing another layer to pass that. And so I don't see like any need of like any kind of a pushing that data in the kernel while you still like need to push that into some shared memory between the hosts. It's very sounds for me like already existing solutions like NVIDIA has VMA, which is allow you basically to replace your socket with a shared memory, which is later controlled with the DPDK or whatever, and make this kind of work to happen. So why we need to fork all the eBPF with possible things that we need a busy polling on the receiver side, because we still need to somehow to announce that we have changed the shared memory and wake up the receiver. And from that case, it's like not pretty much everything is possible except busy polling on the receiver side.
So if I understand you correctly, you mentioned some existing solution with DPDK. So I think that's the problem we try to avoid. So we don't want to change the application. So DPDK is complicated. So if we want
there is a LD preload layer which is actually drops the same way and it works.
Yeah. Actually, LD preload is also limited. For example, we have static linking application. Also, we have some higher level language, like Python or something, right? So if it's not just LD preload will solve everything.
Okay, and the second question. So you still have to do busy polling on the receiver side. So isn't like busy polling is a case that you have a higher throughput on the like in your test, because like the receiver is doing the busy polling actually instead of like waking up.
I don't think it's a busy polling because we plan to replace the socket pooling, traditional socket pooling. Just pull the ring buffers.
Okay.
Yeah, it's not busy pooling. Yeah.
A few things. I think on the last on the summary slide, you had that SMC doesn't have a
like I think it's here in the inter-container communication. So as a comment, I think with 6.10 we now have the SMC loopback variant. So I think that could fill that gap. I know that Alibaba is working on inter-VM communication. I think that's what you probably upstream is working on it with Virtual ISM. And there's the IP proto thing for the LD preload. So are you planning to look more into SMC in that regard?
Yes, thanks for the update. So I think the problem is with SMC is still the LD preload. I know there are some discussions in the mailing list about, override the socket family with some eBPF, but from my point of view, actually, I think that's not very good because we could, all the infrastructure we mentioned here, actually, none of the pieces actually is specific for our case. So for example, for the Shrug Ops, actually, I believe it could also benefit, other cases as well. So the advantage of this solution is every single piece could be reused for many other purposes. So it's not just specific for our case. We just put them together. Yeah.
I think that this overload might make sense. I think for the for SMC with getting rid of the LD preload, I mean that has been like the biggest pain for us for a long time because SMC originated on the mainframe and we use it a lot. And I think now with the IP proto that SMC that was just merged, you can overwrite it with BPF, and I tested that. So yeah, but it's still interesting to have a complete override. Yeah.
Thank you.
Hi, I just want to say thanks. I thought the presentation was really interesting. So thank you for giving the presentation and the information. I was just curious, I think on one of the earlier slides for the VM implementation, you mentioned that there wasn't a prototype available yet. I was just curious, are you planning to, when you build this and you start using it, are you planning to like open source it so that others can like learn from the way this is designed and implemented?
Yes, of course. Yeah, because the non-VM case actually is already available in Selenium. So yeah, and the VM case, if we have a chance, we definitely will open source.
Okay, cool. Thank you.
I was wondering, how does this interact with migration? If you decide that you want to move one of those VMs somewhere else, are you able to get it to sort of fall back to the real TCP?
Oh, this is a good question. Actually, I don't think this could work, for the live migration. Yeah, because I'm, for the once we switch to this one, the TCP socket, they are no longer TCP anymore, right? Yeah.
So I have a difficult question for you. You mentioned that you are willing to support other protocols like HOMA and possibly others. So, but this solution depends on the TCP through a handshake though, right? So, are you like, how would that work? My understanding is HOMA doesn't use TCP through a handshake.
Yeah, this is a very good question. Yeah, because TCP is connection oriented. Yeah, so if the protocol itself actually does not have any handshake, that means we do have some troubles here, because the socket API is not just about the send message, receive message, or but it's also about how we establish the connection with connect or accept this kind of APIs. Actually, I don't have any specific idea for connectionless protocols to leverage this. Yes.
I think the idea would still work. It's just that you have to replace the actual handshake with something else, right?
Yes, I think for the socket operation, we have everything available. I think we also have a hook for connector and also for accept as well. So how to implement this, I don't have any idea yet. Yeah.
All right. Thank you.
Thank you. Yeah. Thank you.